Okay, now we are almost at the very end of this lecture. We will do now Dirac particle. We will now do Dirac particle in presence of a state potential. Okay. So the Dirac equation, so firstly we introduce something usually called Feynman/ notation. Feynman/ notation. And by that, if I have something like this quantity, this usually means gamma mu mu. Okay. So any quantity which is slashed means that it is contracted with respect to the gamma matrices. Okay, so for our case, so we chose conventions so our choice of gamma matrix is the following. Sorry, gamma 0, gamma I, where I runs from 1 to 3, is 0 sigma I minus sigma I 0. Sigma I are Pauli matrices, and this is really a 2 by 2 matrix. Okay, so gamma matrices are 4 by 4 matrices. So then the Dirac equation in presence of a potential takes the following form. Okay, the Dirac equation takes the form I del slash minus gamma 0 v of z acting on the Dirac wave function is m times the Dirac wave function. Okay, so just like in the previous case, we will first discuss again just what happens if the potential is just constant. Okay, what if just the potential is constant, then what happens? So let's take v of z to be sub v for all values of z. Okay, then there are two independent solutions of Dirac equation. One 0 k e minus v plus m 0. The subscript the subscript plus and minus, the significance of that is basically that they denote the spin up and the spin down solutions. So if you go to the rest frame and if you compute the spin of these particles, then this thing will just compute the spin up and the spin down. 0 1 0 minus k over E minus B plus M. Okay, but we do not want, so this was constant potential. But what we want is the solution in presence of not constant potential but in presence of a step potential. Okay, so in case of step potential we will do the same strategy as above, that we will, so let's draw the step potential again. So we discussed, so this is region 1 and this is region 2, and let's say this height is V0. Okay, so in case of constant potential, step potential, we already discussed for Klein-Gordon case that there are three possibilities: weak potential, intermediate potential, and strong potential. That same classification holds also for, I mean, the same philosophy also holds for Dirac particle, and in general it's true for any relativistic wave equations actually. Okay, so this is also true here, and the strategy is again the same. So we will write down the wave function here, psi 1 t of z, and we will write down the wave function here. And in this case we just demand continuity. Demand continuity of psi. So this is also one important contrast from Schrodinger and Klein-Gordon equation, that Schrodinger and Klein-Gordon equation were both second order equation. That's why we have to demand continuity for both the wave function and its first derivative. But Dirac equation is first order in derivative, which means that when we try to impose these continuity conditions, the continuity condition, as long as we just impose it for just the wave function, it is good enough. Okay, so then the wave function in this case is again something like some incident wave function plus some reflected wave function. Okay, let's write. Okay, sorry, I was doing fast. Let's go slowly. So let's define P equals to E square minus M square, and P prime is plus minus. This plus minus sign depends on whether it's a strong potential or weak or intermediate potential. E minus V whole square minus M square. Okay, we discussed about the sign issue for the Klein-Gordon, that the same discussion is true here. Now in our case, the incident wave function, let's say the incident wave function is just have spin up. Okay, this is our choice, that we are only sending that, and it's traveling from left to right, which means our incident wave function is in the same way you can write down the reflected wave function, but in general the reflected wave function can have both the spins, so which means our reflected wave function will be some coefficient a times exponential I e t plus pz. P has to flip a sign because it's reflected. 1 0 minus p e plus m 0 plus b times minus I e t plus pz 0 1 0 P over E plus M. Okay, and in the same way we can also write the transmitted wave function. The transmitted wave function will also have a similar expression where P will be P will be replaced by minus P prime basically, because it's traveling to the positive z axis, but those coefficients are like c times exponential I e t minus P prime z 1 0 P prime E plus M 0 and d times the other part. Okay, I'm not writing. Okay, let me just complete it. Oh, sorry, there must have been a V here. So this is this is E minus V0 plus M, and this is also E minus V0 plus M. Okay, so now again we impose the so that the transmitted the wave function in region 1 is simply the incident plus the reflected, and the wave function in region 2 is simply the transmitted one. And if we demand the condition that this at z is equal to 0, the wave function at z is equal to 0 is same as the transmitted wave function at z is equal to 0, you can easily just solve this thing and you can check that B and D equal to 0, and 1 plus A is equal to C, and 1 minus A is equal to R times C, where R is defined as P prime over P E plus M over E minus V0 plus M. Okay. Good. Now again we can compute the so in case of, again let's go back to the current, the U1 current. Okay, and in this case the Dirac current is defined as just J mu is such psi bar gamma mu psi. Okay, we do the same strategy again. We will compute the z component of the current for incident, transmitted and reflected. Okay, the computation is given in the lecture note. Okay, but if you compute that and then if you put back this expression, you will get the expression for T, which is something like 4 R over 1 plus R whole square, and R is 1 minus R over 1 plus R. Now again the point is that when for strong enough potential, the whole point is that for strong potential, R, small r is less than 0. This implies that capital R is greater than 1 and capital T is less than 0. Is the same conclusion that we have arrived from the Klein-Gordon equation, that if we send something, then the reflected wave is greater than the reflected wave is greater than the incident wave, and the transmitted wave is less than 0. Okay, so it's the same sort of issue that we have got for the Klein-Gordon particle. So what's happening here? Let's try to discuss what's happening here. And the physics is roughly the same for Dirac particle or the Klein-Gordon particle. Okay, So for both of these particles, you remember that the dispersion relation is E square equals to m square plus p square. Okay. Which roughly means that if we try to have energy levels, let's say this is the allowed value, this is the energy diagram. We try to draw the energy in this way. So this is the axis of an energy axis. Okay. Then the allowed value of energy is somewhere in between. So there is a gap here. This is 2m. But otherwise, these are all the allowed values of the energy. Okay. And this regime, this part is not allowed. So okay. So this is the allowed value of energy. And we usually discard this part. Discard this part. Discard negative energy part. Sorry. But here we will see that what's actually happening. So let's say we have this potential, right? We have this potential which has this following form. This is a state potential, which means in this regime, so let's say sorry, let's just discuss weak potential. This is V0. So in this case, E minus V0 is greater than M. Okay, which means we are somewhere here. So the whole point here in this case is that let's say this is the regime. Wait, sorry. I think I wrote something wrong. Let me give a moment. E minus V0 was less than M, I think. So for the strong enough regime, for the weak potential, yes, so E minus V was less than M, so we are somewhere here. Okay, which means that in this part, the allowed energy value is this. Something like this. It's not completely symmetric, so let's draw in the symmetric way. So this is my 2m. So this is my energy level. Actually, let's draw the potential with a different color. Okay. So we are somewhere here. Let's say we are somewhere here. And this was the incident wave, which is less than V0, but it's allowed by this regime because it has, so this is energy E, which is E is greater than, E itself is greater than M, but E minus V is less than M. Okay. Now that means this is the case, and in this regime, so this is region 1. In region 2, these energy levels, these energy levels will be shifted upwards. So which means that in this case the energy levels is somewhere like this. Something like, sorry, I think. These are the allowed energy levels. Okay. Again, this gap is 2m. Okay. Now what happens in the strong potential case? What happens in the strong potential case is the following. So for the strong potential case, we have to draw this diagram carefully. This is very important, strong potential case. So let's first draw the potential. Okay. And then in that case, what happens is that sorry. Let's say this is my this is the energy levels here. Again, this is 2m. And what happens here is that the energy level here, I mean, let's draw this line again. Okay, now, so in this case what happens is that because this potential shifts everything upwards, so the energy level has something of this form. So the important point here, so this is 2m. The important point here is that because of the potential is strong enough, this V0, this shifts the negative band. So let's call this is the positive band, this is the negative band, and this is the positive band. That it shifts the positive band, the negative band so much upwards that the negative band in the region 2 has the same energy with the positive band in region 1. Okay, so this is the positive band in region 1, this is the positive band in region 1, and you see that it has some overlap, I mean overlap in the sense that it has same energy as the negative band in region 2. And when this happens, the physical picture is basically that things can go from here to here. Okay. In other words, what actually happens is that this energy, this potential has so much energy, that is energy is greater than 2m, which means that it gives rise to, it has enough energy to create a particle and an antiparticle. Okay. And this particle and antiparticle is created here. This particle and antiparticle is created here. So this is the antiparticle, this is the particle and this is the antiparticle, because we are studying electron. And the antiparticle, which is positive, this thing travels in this direction. And the particle, which is negative charge, this travels in this direction. Okay. And as a result, since the potential creates pair of particles in this regime, this implies that the incident wave, even if you send incident wave, on top of incident wave there will be new contribution because there are particle creations. Then the particle creation happens from this potential, and that's why the reflected wave is more than the incident wave because of this particle creation business. And for the same reason the transmitted wave is negative, because the transmitted wave consists of antiparticles, so it has opposite charge, so the transmitted wave is negative. Okay, so this is the main reason behind the Klein paradox, that why the reflected wave is greater than 1 and why the transmitted wave is negative. Okay, this is the basic philosophy. Now you see that this is a big problem. This means that particle number is not conserved. Particle number is not conserved. And this phenomena in quantum field theory is usually called as the phenomena of particle production. Okay, this is a very important phenomena. The first computations of this phenomena was due to Heisenberg and later more rigorously done by Schwinger, Julian Schwinger. And the phenomena they studied is that they tried to study the electrodynamics. They tried to study the charged particle in presence of a strong enough electric field in the same way like this, such that the energy density of the electric field was greater than 2m electron c square. They tried to study this thing in this regime, and they found that this leads to particle creation. They actually explicitly demonstrated that. And because of the particle creation, the background electric field decreases because the energy is transmitted from the field to the particle. Okay, but apart from this phenomena, which we will study probably later in this lecture, in this course, try to understand the importance of this. The importance of this phenomena is that it means that strong enough electric field, is not stable. Okay, it decays to pair of particles, particle and antiparticle. Okay, so this is a very important phenomena because you see that classically you can create as large as electric field as you want. Nobody stops you to do that. Classical electric field can be as large as possible, but quantum mechanically, due to this more precisely in relativistic quantum dynamics, the electric field cannot be as large as you want. It has an upper limit, and if the electric field is more than that, it is quantum mechanically unstable and it gives rise to particle productions. So this phenomena should be contrasted with hydrogen atom. So hydrogen atom so this is classical mechanics and this is quantum. So here it was unstable, right? And quantum mechanics made it stable. Here it's actually the opposite story. Here it's strong fields, and here it is stable classical mechanically. In classical dynamics it is stable, but quantum mechanically it's unstable. Okay, and these two phenomena are very crucial phenomena that you should keep in mind, because often you will see that people say that quantum mechanics is dictated by a small constant h bar. And since it is a small constant, the quantum corrections are always very small. Okay, so it is true that the quantum corrections are dictated by h bar, and the h bar is small. But even if these corrections are quote unquote small, but they sometimes lead to drastic consequences. It completely changes the classical picture that we get from classical dynamics, and quantum mechanics completely changes it. I mean, in hydrogen atom, classical mechanics, it was unstable. In quantum mechanics, it's stable. So it's not just, I mean, then one may say that, okay, quantum mechanics increases stability. It's not correct, because here you see the opposite phenomena, that if we have strong electric field, then strong electric fields are classical mechanically very, very stable configuration. But in quantum mechanics, is completely unstable and it decays into particles. Okay, so these are the phenomena which basically tells you that how novel quantum mechanics is, right? Because here the quantum correction is important, and the quantum correction drastically changes the classical picture. Okay, so similarly there is also something called Hawking radiation. there is something called Hawking radiation. And it is the same thing. It's basically strong gravitational field. So Hawking radiation is important because Hawking radiation comes from black holes. And black holes classically don't radiate. They do not radiate classically. Okay, but again the same thing happens quantum mechanically. Strong gravitational field of black hole gives rise to particle production. And this phenomena is known as Hawking radiation. Okay, so this probably many of you heard that Hawking radiation is still a very active area of research, and it is still not completely well understood that how unitarity is restored in Hawking radiation and all this thing. But I would like to just draw your attention that this simple phenomena, that strong electric field gives rise to particle production, this is a very central theme, and it's still a active area of research because Hawking radiation, there is a lot of research going on. And the phenomenon is extremely simple and can be just understood just by studying Klein Gordon equation or just the Dirac equation in presence of a strong potential. Okay, so all these phenomena, Swinger pair production, Hawking radiation, there is also another phenomena called reheating during inflation. All these phenomena have the same underlying theme, and the theme is that particle production due to strong background fields. Okay, I hope you will at some point. I don't know how much time we will get in this course, but you will. You should study this phenomena yourself and try to understand, because these are the novelties of relativistic quantum dynamics. But let's just come back to the lecture material. The important point here is that because particle number is not conserved, there is no way to write these dynamics using quantum mechanics. Why? Very simply speaking, in the quantum mechanical picture, the wave function on one side will have n plus 2 particles. Let's just do the simple case which is studied. So on side the wave function will have one particle. Let's say of the electron. Another side there will be 3 particles. 2 electron and 1 positron. Okay. So now if you try to write down the wave function for these things in the product basis, you can try to do that. And if you try to compute the matrix element between them, you can see that there is no way you can make sense of that element. Because in one the bra will have 3 states and the kate will have 1 state, and there is no way you can do the overlap. There is no way you can make sense of that. The only way you can make sense of this is go to occupation number basis. And in that basis there is a very natural way to increase and decrease the number of particles, and that's why the occupation number basis, or the basis of quantum fields, is a natural language. So fields are the natural language to study relativity and quantum dynamics together. So this thing is actually beautifully explained in much rigorous and much detailed way, with all sorts of new things which are known as the more precise phenomena, that unitarity, causality and relativity. relativity implies quantum fields. This part is very beautifully explained in the volume 1 of Weinberg. Actually, he spends, I think, around 10 chapters just to illustrate this point. So it will be outside the scope of this lecture because it will take a lot of time to discuss that point. But in your spare time or maybe during your vacation, I encourage you to read volume 1 of Weinberg to know this point better. Okay. So this basically ends our discussion of why we should study quantum field theory. In the next lecture, we will go to the formalism of quantum field theory and how various things are defined. And then we will see how we can, we'll first develop the formalism for few lectures and then we will come back to its application again.